Hey guys, it's Dave. My name is Gaurav Mehta, and my group members are Akash Gupta, Bupalapati Naga Adithya, and Shantanu Gupta. And we're going to talk about the compiler construction tools. I've specifically chosen the LLVM based RISC V compiler, and I'll be going through its detailed analysis and through this presentation. Now, before we jump into the compiler construction tools in specific, I would like to give a brief background about compilers. Programmers write programs in high-level languages like C, C++, Java, and Python. Now, this is not in a form that computers can understand. Computers understand machine code. Now, we need a compiler to transform the source code in the high-level language into something machine code. The compiler scans the whole program and translates it into a functionally equivalent program written in machine code. One of the early compilers in the UNIVAC 1 computer timeframe was by computer legend Grace Hopper. She developed a very basic assembler called the A0. Subsequently, in the 1950s, IBM developed the first Fortran compiler, which took an effort of over 18 man-years. This was earlier when compilers were not so popular, and it was believed that humans could code better programs with efficient code. By the 1960s, there were over 40 Fortran compilers available for various machines. At the same time, there were parser generators and compiler tools beginning to show up. Subsequently, Lex and Yak were developed by AT&T for Unix systems. Today, there's a multitude of compiler frameworks available. The GNU framework is widely used and deployed. The LLVM framework is another one that's gaining popularity. There's the Roslyn Apache, MinGW, and ComCert, which are a few compiler frameworks, but they are not as popular as the GNU framework. Now, on this slide, I'm going to be giving you a brief overview of all the compiler tools that I came across during this study. So Mesilang is an open source, non-Java JVM language designed by Samsung. Now, based on the GitHub repository, I could say that the Mesilang community seems to be inactive because the last GitHub commit was 3 years ago. Open64. This is an open source compiler suite supporting Fortran 77 or 95. C, C++ for x86-64 MPU, and now defunct Intel Itanium architecture, which was not so popular. Then comes ROSE, which is an open source compiler infrastructure for building source-to-source program transformation and analysis tools, aimed at non-experts to leverage compiler tech to build their own custom software. Then comes Roslyn Apache, which is an open source compiler infrastructure for C# and Visual Basic .NET languages from Microsoft under the Apache open source license. Then comes MinGW. Now, this is an open source software development environment to create Microsoft applications. However, the project has faced inactivity due to the introduction of an alternative project called MinGW W64 meant for 64-bit systems. Then comes CLisp, which is an implementation of the programming language Common Lisp, originally designed for the Atari ST in 1987. It's now expanded into an interpreter, bytecode compiler, debugger, socket interface, along with many other tools. Today, it's a part of the GNU project. Then comes ComCert, which is a formally verified C compiler and targets x86, x86-64, PowerPC, and RISC V architectures. It's founded by a French man named Xavier Leroy in 2005 and is funded by French organizations like ANR and INRIA, which is the National Institute for Research in Computer Science and Automation. Now, before jumping into the C compiler architecture, at a very high level, I want to show you how the compiler works. It starts off with some source code, which can be written in C or any other high-level language, which undergoes some pre-processing, some lexical analysis, syntax analysis, and semantic analysis, out of which comes an intermediate representation, or IR, format. Now, IR basically does the IR optimization on itself with several passes in this domain and produces another IR code, which is more optimized. Then comes the target code, which is produced from in the latter stage, which is meant to target the targeted architectures like be it RISC V, be it x86, be it ARM or A series, which you can take and run on the target platform. Now, most compilers today, if we look at them, have multiple faces or a modular design. At the very beginning, we usually have a C code and the preprocessor directives, and this is processed, after which an IR comes out as the product. The IR is a lower level representation of code. Then in the middle comes the optimizer, which takes the IR and optimizes it through several passes and produces an optimized IR format. The optimizer looks at various ways to optimize the code, like loop invariant, loop unrolling, dead code removal, and several other techniques. Then comes the backend, which takes the optimized IR and maps it to the target architecture, be it x86 or RISC V or ARM. Now, as we've talked earlier, the compilers earlier were really simple because they didn't have the larger memory that we have today. I believe that during the UNIVAC timeframe, the UNIVAC one was one of the largest machines at the time, but only had 1,000 words of storage. Hence, the compiler codes had to be designed in such a way to fit 1,000 words and at the same time work on the program code. Now, due to this, the early day compilers used to be run in different places, in different phases. So when the first phase would complete its analysis on the code, the second phase would be loaded and run. Upon completion of the second phase, it would move to the third phase and so on. It divides the compiler process into smaller stages to fit the compiler. Modern compilers have not changed much in this perspective. There's still a multi-phase implementation for the compiler. However, there is a change in the way that the compiler process runs. We do not load one compilation phase at a time. Instead, we load everything together. The multi-phase approach also has a bunch of benefits. Like when the software is modular, it's a lot easier to maintain and update. It allows for a lot of views between different compilers, which we look at in the next slide. It also allows for support for multiple high-level languages quite easily and multiple target architectures quite easily because it uses modules, which you can pick and choose and leverage common modules like optimization module, which is fairly complex to use across HLLs and different architectures. Now, this is what an LLVM architecture looks like at a higher level. As we've seen earlier, there's a front end, which is language specific, like the Fortran front end, which was designed by Peter Penzin, the C front end, which is designed by Vikram Adve or Chris Latner, and the ADA or ADA front end, which is designed by Michael Larabelle. Then comes the common optimizer. Now, the front end converts the source code into the intermediate representation format. Now, the common optimizer takes the IR code, runs a bunch of passes on it, and produces an optimized IR. Then comes the backend. The backend produces the target code for the particular architecture, and it is machine specific. The backend converts the optimized IR into target specific code based on the architectures listed on the slide. As we can see, it can be for x86 backend, which is designed by R.K. Simmons. It can be for RISC V backend, designed by Alex Bradbury, or it could be for an ARM backend like designed by Christoph B. or Gaber B. Now, the LLVM compiler uses an intermediate representation format. Now, this is the heart of the compiler. Common languages used by LLVM modules to represent the code. It is lightweight, it is efficient, and it is easy to understand. It's quite similar to assembly code. Now, it is also fully typed, and the type checks are rigorously implemented. It also has full support for vector and SIMD data types, which can run on vector machines and SIMD machines. It also has full support for GCC style inline and assembly. Now, also a point to be noted is that the registers use SSA, which is static single assignment, which means that there is an unlimited number of virtual registers. Now, this virtual architecture is low level enough so it can be related to the hardware operations, but also it's high level enough to include the high level control flow and data for sophisticated analysis and optimization. Now we can look below and we can see a code snippet, which actually represents the C function, which is used to compute the power of a number. Now the snippet below is in an intermediate representation format, and as we can see, it's pretty easy to understand. And it's also similar to the assembly code. So In this slide, I'm basically showing two very popular compiler architecture models. On the left, we have the Aho-Ullman model, which is used by the LLVM compiler and the LLVM framework. On the right, we have a Davidson-Fraser model, which is used in the GCC compiler. So over here in the Aho-Ullman model, we can see a modular design, which is divided into the front end, common optimizer, and the back end. On the other hand, in the Davidson-Fraser model, which is used by GCC, we can see a HLL front end or high level language front end, followed by code expander, code combiner, and code assigner. And the thing is, Davidson-Fraser model uses RTL, which is register transfer language. And this is architecture specific, and hence the reuse across different compilers is fairly limited. Now I'll try to compare these two compilers based on two compilation phases, which is the instruction selection and the optimization. So in the instruction selection, we can see that both the Aho-Ullman model and Davidson-Fraser follow a similar pattern up to a certain extent. The machine-independent IR is expressed in the form of the AST. The target machine instructions are expressed in trees, and the trees in the IR format are covered by using target instruction trees. Now the difference is that the Aho-Ullman model uses cost-based tree pattern selection, while the Davidson-Fraser model uses structural tree pattern selection with no optimization for instruction selection. Moving on to the optimization phase, the IR format optimization or machine-independent optimization is where most of the optimization takes place in this particular phase. While in the Davidson-Fraser model, most of the optimization has taken prior to this, and now they're machine-dependent optimization and register transfers, which are more target-specific. So the RISC V compiler. So the RISC V is one of the newest open source CPU architectures developed by UC Berkeley, and it's gaining popularity because it's an open source compiler. Today, there are several companies, more than 100, out of which a few names are Google, Intel, NVIDIA, and Qualcomm, which are members of the RISC V Foundation. The RISC V Foundation was set up in 2015 to promote and collaborate innovators in the hardware and software ecosystem. And there are several compilers supporting the RISC V architecture, including GCC Clang LLVM, CompCert, and the commercial compiler infrastructure, IAR. Okay, so the Clang front end. So a bit about the history of the Clang front end is that the company Apple, the very popular company Apple, made extensive use of LLVM in a number of its commercial products. Now, initially, it tried to use GCC as a front end, but this caused problems to the developers of LLVM at Apple. The code was large and it was cumbersome for developers to work on. And hence, this led to Apple to develop a new compiler front end from scratch that supported C, Objective-C, and C++. The Clang project was open sourced in July 2007. Now, this is the front end of the compilation process, and it involves 4 smaller stages, which is pre-processing, which includes the macro expansions, hash include expansions, and other preprocessor directives like hash define, hash if def, hash if, and so on. Then comes the lexical analysis, which involves converting the high-level code into tokens and creating a symbol table. Then comes syntax analysis, which involves with using the tokens and context-free grammar and the production rules to perform syntax checks and generate an abstract syntax tree, as we talked about before. Then comes semantic analysis, which is use the ASTs and the symbol table to perform type checking, label checking, and flow control checks. This phase of the compilation generates errors and warnings. The LLVM optimizer transforms the IR format input into an optimized IR format output. And this is the same format. There's no change in format that takes place in this phase. However, maximum of code optimization takes place here. There are various algorithms like the p-poll optimization, which looks at a smaller chunk of code and looks at adjacent instructions and replaces it with something faster. There's also local optimization, which works on a block of code locally and performs stuff like local constant propagation, data assignment removal, sub-expression removal, redundancy removal, and local value numbering. There's also global optimization, which works on the entire procedure and uses control flow diagrams and data flow diagrams to optimize the code. Now, this takes place over the full code, And some of the techniques used over here are loop unrolling, optimizing loop invariant calculations, induction variable elimination, and code inlining. Okay, so the backend is the last phase in the compiler. The backend receives optimized IR code and symbol table as inputs and generates an optimized target code for a specific architecture, in this case, the RISC-V, as output. Now, the main functions performed by the backend module are converting IR format or the 3-address code to target specific instructions with the lowest cost, which can either mean low size or great performance using any of the instruction selection algorithms, which are table-based or subtree matching, etc. Now, it has to allocate memory to the register, stack, or global storage for optimal performance. The backend looks at the CPU architecture and availability of resources within the CPU and the system, and has to come up with an assignment for register, stack, and storage specs with this optimized target code. In this phase, because the backend is tuned to a specific architecture, it has a fairly good understanding of how the CPU works and how the CPU pipeline and resource allocation work. Because it understands the intricacies of the CPU, it can schedule the instruction to give the best performance. In addition to generating target code, there's also debug data, which helps in debugging of the code. So there's no perfect compiler, and there's always scope for improvement. So let's look at some of the pros and cons of this compiler. So let's start with the pros. We can reuse, enable deployment of new compilers with relatively less effort because of the modular design. There's also support for new and emerging languages like Swift and Ruby, which are available. There's aggressive optimization like loop unrolling, unswitching, mem promotion, using various algorithms and techniques. There's also more accurate and friendly diagnostic info available, which helps with faster debugging. The availability of useful tools like editor plugins, scan build, static analyzer, and BugPoint help with productivity. BugPoint is a tool that narrows down the source of problems in LLVM. It can identify 3 problems like optimizer crashes, the miscompilations about the optimizer, and bad code generation. It does so by reducing large test cases into smaller test cases. There's also the support for extensions like threat security check and other extensions, which help make the code robust. So listed on the right are some of the cons. There is a lower performance relative to the more popular GCC. There are also fewer architecture support compared to GCC or other rival compiler architectures. It's not as widely used as GCC because it's a more newer architecture and it's also not as widely tested. There is a relatively small community as of now, but it's a fast-growing one. So in conclusion, I'm going to list a few things out that we've covered in this presentation. We have reviewed the development of compilers and compiler construction tools. We've reviewed the multi-phase compiler architecture and its benefits. We've explored and analyzed different phases of the compilation and tasks within each phase using the RISC-V LLVM compiler as an example. Detailed review of IR format and its significance to the LLVM architecture. We've looked at some of the pros and cons, and we've analyzed them for this LLVM compiler technology. And in short, the compiler development is an exciting technology with several interesting challenges in front-end optimization and back-end. I'd like to thank our professor Aruna ma'am to give us the opportunity to look at this compiler, this practical and pragmatic compiler in depth and understand more about how compilers work today and how the open source community functions. Thank you.